to push that button, which is going to keep me honest. So, consider the case of the statistician who drowns while fording a river that he calculates is, on average, 3 feet deep. If he were alive to tell the tale, he would expound on the flaw of averages, which states, quite simply, that plans based on assumptions about average conditions usually go wrong. Today, we're going to talk about pain. We're going to talk about water, and there's a dinosaur in here somewhere as well. On the morning of July the 13th, 1995, all was well on Coast Guard Station Marquette on Lake Superior, one of the Great Lakes in North America. The Coast Guard does a lot of things, but one of the somewhat lesser known jobs of the Coast Guard is to measure water surface levels. Back in 1995, the measurements were taken every hour, and this data was then averaged to show the mean water level per day. Nothing was out of the ordinary, with the level showing a slight slow upward trend around 180.36 meters. And that trend is quite normal as the water level fluctuates somewhat, and it peaks between June and August. But today was going to be anything but ordinary. The wind had been blowing rather constantly for a while, and this was creating an event that surprisingly few people know about. Over the span of 15 minutes, the water level fell and then rose again 3 feet. That's about 1 meter. 350 miles away in Port Huron on the shore of Lake Huron. Over the course of 2 hours, that level changed 6 feet, or almost 2 meters. The phenomenon is called a seiche and occurs when a squall line with high winds drives water across an enclosed body of water, such as a lake or a coffee cup. Could have been prevented? No, not in the slightest, because this is Mother Nature we're talking. Could it have been predicted? Yeah. Oh, yes, absolutely. But definitely not by looking at the darn mean. Why would I want to? Well, in 1995, nobody was killed. On June 26th, 1954, however, 8 people fishing on the pier in Chicago were pulled away by the 10-foot waves, that's 3 meters, perishing in the water. My name is Alexander. I have 25 years in IT, pretty much all of it spent with data, databases, infrastructure, some way, shape, or form. These days, I work for a company called Solution Experts in Sweden, and I make data matter because only data that truly matters can inspire any change. One of 7 data platform MVPs in Sweden. I am a certified trainer, and I co-host a podcast called Meet It in Tech. And yes, that is the Doom Game logo. Let's look at a few ways averages or means hide important aspects of data. 3 complete different data sets can display the same mean but have vastly different data points. For example, if you want to look at the height of students in a class like this data, well, the average height is going to be the same in all 3 classes, but the individual student height is going to be very different because the mean won't show you the spread of the results. Well, kind of sucks. Let's look at another example. I wasn't always in IT. I used to be a paramedic, and hence I know a bit more about pain than the average guy. See what I did there? A common way to quantify pain is to ask patients to rate their pain on a scale from 0 to 10, where 10 being the most excruciating pain they've ever experienced, and 0 meaning no pain at all. Since pain is impossible to measure objectively, this self-appraised number is extremely important to track pain development over time. Just as we saw in the previous example, we can have 3 different sets of data, i.e. groups of patients, who all exhibit different levels of pain. But on average, they're only complaining about a slight pain. No sane doctor would treat them all based on this average, right? Of course not. But that's exactly what averages will do to your analysis. In the previous example, the results were spread over and, well, above and below the average. However, this is not always the case. As we saw, one data point can have a large effect on the average of the entire set. Here we have the same average, 5, But going back to the pain example, let's look at changes instead of absolute values. Let's say we're doing a study on pain medication, and we have two groups of 100 people each. For the first group, for 99 people, pain improved by just 1 point. And for one person, pain improved by 5 points. In the second group, 99 people, pain improved by 1 point, but for one person, pain worsened by 5 points. The average is 1.4 point improvement in group 1 and a 0.94 improvement in group 2. Based on the mean, well, the treatment in group 1 looks better, but in reality, for 99% of people, both treatments are equally effective. In this case, the mean is completely misleading since two people with extreme results are pulling the average up or down, so it does not represent the population as a whole. This is what happens when there is a skewed distribution because of extreme outliers. In a similar way, two groups can have the same mean result even though most participants do better on the first treatment, but there's just one person, one patient who does really, really well on the second. Another way in which the mean can be misleading is that it does not give us information about how a patient's improvement relates to whether they had an important or noticeable change. Sometimes this change is referred to as the minimum important difference. And if we only look at the average, the above group seems better than the group below because they had a 1 point reduction in subjective pain on average compared to only 0.8 in the group below. However, if a minimum 3-point change is needed to be noticeable in the patient, well, no patient in the above group experienced a noticeable change, but two people in the group below did. In terms of the proportion of patients who have an important improvement, well, the below group is better than the group above. The average in this example is misleading, again, as it does not show which patients have an important change. When the average is higher in one group, it does not necessarily mean that the treatment for that group was more effective, since most patients do not experience the average effect. Funny that. My personal favorite is expressing qualitative data as numbers and then trying to do an average or a mean of that. Let's say that a bicycle equals 1, an orange equals 2, and a rather upset dinosaur equals 3. What would the mean of this represent? Well, you tell me. But I've seen this very phenomenon in customer data, and let me tell you, it is confusing. So, in conclusion, it is vital to know your data, and what I mean, well, means. If the spread of the results is uneven, the average can be influenced by extreme results, making the effects seem larger or smaller than they really are. Moreover, as we saw in the example with pain, the average does not give us information about which patients have a clinically meaningful improvement. Averages will inevitably hide many important aspects of your data, and try to go for this one number and base calculation off of that will take you back to the flaw of averages. Remember that plans based on assumptions about average conditions usually go terribly wrong. Instead, look at a histogram or other visual displays to see how the results are spread. Look into what defines a meaningful change in the scale. Look at what percentage of the data points achieved that minimum important difference. And that brings us to the conclusion of the story that I began with. Had the Coast Guard, instead of looking at the averages, been looking at the standard deviation, a clear and sudden variation in surface level would have become evident already on the 12th of July. And this is indeed one of the methods used today to predict seisures. My name is Alexander. I am not a fan of averages. Thank you for your time.